Hello, and welcome to this lesson on the trends of the noble gases. In today's lesson, we will firstly examine the boiling point of noble gases and how these boiling points change as we move down group 0 of the periodic table. Secondly, we'll explore the reasons behind the observed trend by discussing intermolecular forces and how they vary with the size of the noble gas atoms. So far, you have become familiar with the noble gases located in group 0 of the periodic table, and you understand their valence shell configuration, which is full, making these elements exceptionally stable and unreactive. Building on this foundation, today's lesson will enhance your understanding of why the boiling points of noble gases show a specific trend. Let's start. Let's delve into the boiling point trends of noble gases in group 0 of the periodic table. Understanding why these trends occur can help illustrate broader principles about atomic structure and intermolecular forces. We'll look at 3 reasons as to why the noble gases have certain boiling trends. Firstly, noble gases have low boiling points, which is why they are gases at room temperature. This is linked to their atomic structure and the types of forces that exist between their atoms. Secondly, their boiling point increases down group 0. When you look at the periodic table, you'll notice that as you move down group 0, from helium, He, to radon, N, the boiling points of noble gases increase. This trend is systematic and can be attributed to increases in relative atomic mass and atomic size. Let's consider why their boiling points may increase down the periodic table. Building on the previous point, the difference in boiling point of noble gases is due to their relative atomic mass and atomic size. As you move down the group, the relative atomic mass of the noble gases increases. For example, helium at the top has a much smaller relative atomic mass compared to radon at the bottom. Along with the increase in atomic mass, the size of the atoms also increases. This is because more electron shells are added as you go down the group, making the atoms larger. Now let's look at the intermolecular forces of these noble gases. Each noble gas atom is generally non-reactive and exists as individual atoms, not molecules. The forces between these atoms are weak, and these weak forces are directly related to the size of the atoms. Larger atoms have stronger forces. To turn a noble gas from a liquid into a gas, which is known as boiling, enough energy must be provided to overcome these weak intermolecular forces. As we move down group 0, the atoms get larger and their intermolecular forces become stronger. Consequently, more energy, which in this context means a higher temperature, is required to overcome these forces to convert these noble gases from liquid to gas. This explains why the boiling points increase as we move down the group. By understanding this trend, we see a clear demonstration of how atomic size and intermolecular forces play a vital role in determining the physical properties of elements, in this case, the boiling points of noble gases. Great work! That's everything for today. In today's lesson, we learned that the boiling points of noble gases in group 0 increase as you move down the periodic table due to their increasing relative atomic mass and atomic size. We also saw that the increasing boiling points of noble gases down group 0 are due to the progressively stronger intermolecular forces between larger atoms, which require more energy to overcome. This lesson has built a strong foundation for recognizing how atomic structure affects physical properties. See you in our next lesson.